Alright, welcome. So, let's see what do we know so far. Now we have read Schrödinger's equation, and so we know that psi are the wave functions that represent the wave and particle nature of quantum particles. Also, we know that psi is a continuous function because obviously Schrödinger's equation is a second differential equation and we have to differentiate it, and so for a function to be differentiable it should be continuous. So this is not a continuous function, as you see this break. Now next, it can be differentiated two times. Okay, so from one time of differentiation you get a slope, and from the second time of differentiation you get a defined slope, right? So here you see that in this kink, I would say, in this kink the slope is not defined, and so this function particularly here, it cannot be differentiated two times. So psi will not look like this at all. Instead, it must look like this. It can go to 0 also. It will never go infinite, so it will again go to 0 as r. Now let's move again. This is also how it should look like. Where psi touches 0, this portion is called node. Okay. Now this here is not a node. When psi approaches 0, when r is not 0, that is the definition of a node. So this is a node and this is not a node. Moving on, we also learnt about normalization. Now what is normalization? Well, we know that we use psi square as a measure of intensity, or you might say the probability of a particle to be found at a particular place. Now we know that this right here, that is psi, and psi conjugate, that is if it is an imaginary number, then the conjugate of this number multiplied by d tau, which is volume, should be 1, and similarly psi square d tau should be 1 if psi is a real number. Now in both of these cases it is coming out to be 1 because the probability of finding an electron between the whole space has to be 100%, and that's mean 1. Now let's move on to the current topic, that is quantization. So what is quantization? Now as we know that psi has some values, it has actually many values are possible for Schrödinger's equation. You solve it and you get many values, and most of it we ruled out during the normalization. If they do not follow this condition, then they can be removed. Now there is another condition, that psi cannot approach to infinity. So psi cannot go to infinity. So this property is called quantization. Let me just highlight it. So this property is called quantization, that psi cannot approach to infinity. There are two reasons for that. First, if psi goes to infinity at any point, then the probability, that means this function, will not be 1, right? Because we are integrating from minus infinity to plus infinity, and if anywhere psi go to infinity, then this condition will not be followed, and hence psi cannot go to infinity. Also, even if we say that a function is normalized and psi is defined as a normalized function, that is n psi, and we can say that psi approaches to infinity, but when psi is at infinity, n is 0. Okay, so in that case, even if psi is infinity, at that moment this n will become 0, and 0 multiplied by infinity, well, that will be 0 again, and hence we are saved. Well, not quite, because if n is 0 at any place, then it has to be 0 at every place, and the whole function will just become 0, and so that's why we cannot count it. This reasoning is given in Atkins physical chemistry. You can check that out. Anyway, let's move on. Our next topic is observables. Now what are observables? Well, we know we are talking about properties of particles. From the very beginning we are considering that the particles will have some properties described by these wave functions. Well, what kind of properties? Well, as we know, we are reading quantum mechanics, right? So in quantum mechanics, what do we read? We read velocity, position, and what else? Momentum, and what else? Energy, and what else? Mass, maybe, and so on, so on. There are many: moment of inertia, magnetic moment, many quantities. So these quantities, these are called the measurables or the observables because they can be observed through some experiments, through some instruments. So these are called observables. So we have got velocity, position, momentum, energy, mass, moment of inertia, magnetic moment. These are all properties that a quantum particle can show. Wait a second. I is shown by system of particles. So this is not countable. So observables are all these properties that a particle can show. Now, moving on, how do we find these observables when all we know is just psi? So we know psi from h cap psi equal to E psi. So to solve this equation, we must first know E. So E is like first you must know E, and after you know E, then you can find psi. And after you know psi, then you can find any of these other things. But how do we do that? Well, the answer is we do that by operators. Now, what are operators? Well, as you have guessed by now, and operators are something that takes out the information from psi and gives you the value of observable. Okay, so what are operators? Operators are things that operate on psi and you get the observable or the quantity that you are measuring. So there are many operators depending upon how many observables you have. Let's just denote a general operator by the letter omega or the small letter omega. Okay, so let's just denote the operator by omega cap and the value of observable as omega. Now let's see how do you write this. So we are performing some activity with psi, we are doing something with psi and we get observable. So this action is called the operation and it is denoted like this, that you operate on psi. Here it means that you are operating on psi. It means like you are doing something with psi. For example, this right here, it means that you are taking the root of psi, correct? This means that you are finding the root. So here the root is an operator. Okay, so this we have some certain symbols for that. Similarly, this right here, this is also an operator. We are operating on psi and it means to multiply psi with psi. This is the operation means. Anyway, so here what we are getting, let's see. So you take some operator, you operate on psi and what you get? You get the value of observable, that is omega. It has to be real value. And you again get psi. Yes. So it is how it is. Okay. The operator is such that when you operate on psi, you get a real number and psi back again. This kind of equation is called an eigenequation. An eigenequation means where omega has to be real. Of course, I mean, come on. When you are finding an observable such as energy, so the energy has to be real. 2 joule, 3 joule, 4 joule, whatever. The answer has to come. If it doesn't come, then it means, you cannot have imaginary values for energy. So every wave function, every operator has to be such like that you get a real value. So such functions are then called eigenfunctions, and such values that you get are called eigenvalues. Yeah, this was the scientist who gave all these names, so you have to go by his name again. So eigenfunction is a function that follows an eigenequation, and eigenvalues are the values of eigenfunction when you perform some action using operators. So there are many kind of operators. Let's see. So for like we have momentum, right? So how do we find momentum? Let's say first define its operator, that is, let's say p cap. So when you use p cap on psi, so you will get p and you will again get psi. So what is the operation here? I mean, here we know how to take root of suppose y. So how do you find root by that factorization method? You can find it. How to operate this? Well, it's simple. All you need to do, p cap psi means you are multiplying with h cross by I and then differentiating psi once with x. Okay. So for momentum in x direction, you multiply by h cross by I and then differentiate d psi by dx. Your answer will come out to be the value of momentum and psi again. Understood? Yeah, pretty much. That's how it is. Now, let's see. What else? Okay, let's find position. So, position of psi. How do you find position of psi? Well, you multiply with x and you multiply psi. The value you will get is x psi. So that's how it is. Very simple to find position. All you have to do is multiply with x. See, simple. Now, how do you find energy? You multiply with the h cap, that is the Hamiltonian operator, and you get psi. Now, this is something complicated. What you need to do is multiply by minus h cross square upon 2m, then operate on psi by second differential of psi with x in bracket plus second differential of psi with y square, then second differential of psi with z. Oof, this is complicated. Then you add the potential energy. This is all kinetic, okay? This is kinetic energy. Then you use potential energy on psi. That's it. Then you get the value of energy. So that's how you obtain energy. So yeah, you guys did right. This right here is well, let's color it. I didn't like the color. Okay, it's okay. Yeah. So this right here is the kinetic energy. So this is how you find kinetic energy. There is more. So for kinetic energy, let's say k cap psi, you need to multiply by h cross square by 2m, and then all this you can just summarize it in Laplacian operator delta square psi. This and this right here mean same. So here you will get the value of kinetic energy and psi again. And yeah, potential energy lastly. How do you get potential energy? Well, you multiply by half k x square with psi, and that's all you get. So half k x square will be your potential energy, the V, and you get psi again. Simple. So that's how you do it. Now you know what observables are and you know what operators are and how to use them. We can take an example, but maybe that's for another video. Thanks for watching.